Hello, I'm Angela Metler. I am an administrative assistant in the president's office at Dakota Mines. Welcome to STEAM Cafe for September. Thank you for attending on this Wednesday. We had to bump it up a day, or bump it back a day, I should say, due to a scheduling conflict yesterday. Normally, we do this every third Tuesday. STEAM Cafe is a partnership with Camp and South Dakota Public Broadcasting. So we thank them for their support, and we thank all of you for attending, and also our online audience. We will get the chance to ask each presenter questions about their presentation tonight. If you're watching online and you have questions, go ahead and type the questions into either the chat box or the Q&A, and I will ask them to the presenter live. If you're in attendance, go ahead and ask at the end of the presentation when the presenter is taking questions. Yeah, that's all I got. So without further ado, Walker Research Group.
Awesome. Thanks for coming tonight. I really appreciate you guys attending, especially if you're here online. I appreciate your attendance there too. My name is Travis Walker, and I'm going to introduce, spend just a couple of minutes introducing my research group tonight. I really appreciate getting the opportunity to come and give a talk. When I was asked to come and give a STEAM Cafe, which I've attended before, I asked what topic would they like me to talk on, and they said, well, what research do you want to talk about? I said, well, I have a lot of different research going on in the group. And I said, what if I just asked my grad students to come in and give you guys some briefs on the different research that we're doing? So I reached out to my group, and we have 3 volunteers that are here tonight that are going to be talking about the different research that they're doing. So it'll be little short blips on what the different research that we're doing, but you're welcome to ask questions. This is our research group from this summer. We usually have somewhere between, 15 to 20 students that work for us at a time. That includes during the summer. This summer, this was our group. So let's see if I can get this. I'm going to advance. All right, sorry for the technical difficulties. So we're going to have 4 different talks today. I'm going to give you a brief introduction about myself. I was born and raised in Winter, South Dakota, if you know where that is. Came to South Dakota School of Mines here in 2003. Got degrees in chemical engineering and applied mathematics in 2008. Went to Stanford, got my PhD there in chemical engineering in 2013. And then right out of grad school, went to Oregon State, started a faculty position there as an assistant professor. We were there for 4 or 5 years. I also was a faculty material science program. And I also had a position as a member of the quantitative oncology program up at OHSU. In 2017, we started a consulting business, and that's my first foray into entrepreneurship. I'll talk a little bit more here in a second. In 2018, we came back here to School of Mines, where I've been an assistant professor. Recently got tenure, so now I'm an associate professor. I'm also faculty of the biomedical engineering program and the materials engineering and science program. And just this year, then we've actually spun up a couple of companies that are now official, so I can actually put them on the slide. I'm part of a member group here in town that's looking at some real estate to try to bring more research and more technology companies to the area. There's a company that you're going to hear a little bit about tonight called Amber Aqua that's going to be going first with one of my students. And there's another one called Disapex, which you won't hear about tonight, but we might come in and give you another talk about it another time. So my research group consists of a number of different people that study a wide range of different backgrounds, different topics. My group is in collaboration with Dr. Katrina Donovan, who's here in the audience. She's actually also my lovely wife. She's given a couple of these STEAM cafes in the past on additive manufacturing and art and engineering. This is our chance to jump into the different research that we're doing in the group. We study areas of energy, health, and environment, and we're going to get a little bit of each area tonight. We do a lot of work with trying to use models, but we do a lot of experiments in our group as well. And so tonight, a couple of the areas that we're going to be talking about. The first one is going to be on anaerobic digestion. The second area is going to be jump into a type of additive manufacturing that we're excited about. And then another area that we're going to talk about is on vascular grafts and stents. So I just want to do a quick introduction of my research students. My 5 PhD students are here up on the board, and they're also in the audience. 3 of them are going to be talking tonight. But the thing that I really pride myself on in my group is that we have a very diverse set of people in our group. We bring in all walks of life, and we just ask them to just do what they do best. So I like to hire people that know things I don't know anything about. And so you'll see that tonight when they're talking about the different areas. We have people that have backgrounds in chemical engineering, mechanical engineering, people in chemistry, people from biology, and people even from like civil engineering in our group. We've had medical doctors in our group in the past, industrial engineers, design engineers. And so what I like to do is find people with interesting backgrounds. They come in, they think I'm supposed to be teaching them, but what ends up actually happening is they end up teaching me. And that's what gets me excited to go to work every day. So today you're going to hear from Maryam Amouamouha first, and she's going to be talking about amber aqua, and then we're going to jump to Sebnem Ozbek, who's going to be talking about cold spray technologies, and then Brunmaier, who's going to be talking about her work with tissue engineering. So Maryam, you should be able to share your screen. So the first talk tonight is going to be from Maryam Amouamouha. She's a PhD candidate in chemical and biological engineering. She also already has a PhD in environmental engineering, and she's going to be talking about our foray into anaerobic digestion and this company that we've deemed to be Amber Aqua. Thank you.
Thank you, everyone, for being here tonight. And I'm Maryam Amouamouha. I have a PhD, as Travis mentioned, in civil and environmental engineering, and this is my second PhD in chemical engineering. So Amber is a wastewater treatment system, and what we are trying to do is to solve some
It's just going to be delayed, isn't it?
So Amber is a wastewater treatment system, so it's going to deal with water and wastewater. When we talk about water, we have 2 issues. For water, we have a water shortage, which you probably have heard of it. It's a problem worldwide. When we think about it, we probably think about more areas in less developed areas in Middle East, in Africa, in places like that. But it's here. Even in the US, you have a water shortage. We can see in the NASA satellite observation from 1999 to 2021 that how Lake Powell has changed over time. You can see that this lake that is using for recreation, for delivering water to lower basin in California, Nevada, Arizona, and also for the generation of power has been changing and decreasing. The level of water is decreasing really dramatically. So we need to do some some action on this. We also have a problem with wastewater because wastewater is basically water. So it's a precious source of water that can be reused and recovered. For amber, at this point, I'm just focusing on residential side. You can see that 20% of the households in the US, they don't have access to central sewage system. So they are using a septic system, which is not treating wastewater. It's just storing wastewater, and the wastewater goes to a drain field, as you can see it here, and then spread out to the ground, and finally go to the groundwater or probably surface water. So what we have is 4 billion gallons of water per day go into the ground instead of being reused and recovered, which is a lot. And it has some problem, like with the, it's not an enough treatment, so there is pollution inside still. It's going to contaminate other resources that we have, like soil and groundwater and surface water. So that's why we need to do something about this. And the solution that we developed is a system called anaerobic membrane bioreactor with electrolyte regeneration, or AMBER. AMBER is a standalone turnkey technology. It's a zero discharge technology that is using a combination of biological and separation technologies. So it's basically integrating every technologies that we have in wastewater treatment. It uses chemical processes, biological processes, electrochemical processes, and physical processes. This is the MVP of AMBER that we manufactured and installed in Sioux Falls in steel company facilities. So how AMBER works? AMBER, this is the schematic of AMBER. You can see that wastewater comes in. It goes into a electrochemical biological step in here. It's a combination of 6 different processes that happens in one reactor. So it's an anaerobic digestion, but it's being modified and being compacted. And then it goes to, after that, when the whole organic load here turns into biogas, and the water comes out, and also compost. The water comes out and go to a membrane filtration. This membrane cell is a nano-composite membrane. So it's supposed to take out whatever has come out from the biological step here, which is mostly suspended solids and microbial load. So AMBER takes a wastewater treatment, the wastewater stream, and turns it to clean water, biogas, and compost. And in my second PhD, we are mainly focused on the membrane here. What we do is we are trying to actually develop our own membrane, which I will show you later what process are we using. So AMBER has been developed in 4 different phases. Now we are in phase 3. Phase 1 was just the implementation of an anaerobic membrane bioreactor. And then we added to that phase by using an anti-biofouling membrane. It was a modification of the commercial membrane that we have now, which we are trying to produce that membrane and fabricate it in our lab. The phase 3 that is AMBER now, we added electrolytic regeneration to AMBER, so we can eliminate the application of chemical in anaerobic digestion. Phase 4 will be AMBER integrated with the microbial fuel cell, just to turn biogas into electricity. So you can see here, if we consider AMBER as a black box here, you can see that wastewater and some energy that we need to run the pumps and also to heat up the system and stuff like that goes in, and then the AMBER will turn that to some energy, compost, and water. So this is Amber, the second version of Amber that we built and ran here for 4 months. This is the process diagram of Amber, and this is the quality of inlet and outlet just inside the biochemical processes of Amber. And this is the commercial MVP that we designed and we installed. So this is the development from the first version back in my home country, and then this is the second one. We ran it for several months, and then we developed the commercial size of Amber, and we are going to run it in real-time wastewater. Not in the lab, just actually using the wastewater that mimic wastewater from households. So this is the nanofiber membranes, the thing that I mentioned. We are trying to produce the membrane, so just to make a cheaper, more frugal option, and also we can play with the properties that we want to make it more efficient. So this centrifugal system that you see here, it looks like a cotton candy machine. So the polymer solution will go inside a reservoir here, and then through a centrifugal force, it will be spun, and the nanofiber will produce, that you can see here. This is a nanofiber that we produce. So this is for mass production of membrane. This membrane can be used in different industries, not just in water and wastewater. We want to use that in water and wastewater, but these membranes can be used in air filtration, in textile industry, and in other industries. So, and they are going to be a lot cheaper than what we have now in membrane filtration industry, that they are selling this commercial membrane through chemical process. The problem with these membranes are biofilm formation and the poor mechanical properties, but we have solution for that. The first one will be resolved through integrating of membranes with antimicrobial agent. The second one will be done through heat pressing of the system. So this is the result of Amber that you can see. Amber is doing very great in removing organic load, in removing suspended solids. That, as you can see, if you compare Amber with what we need as the standard requirement for wastewater treatment, the turbidity and the ecolor. You can also see the membrane surface after treatment with Amber. And this is the publication that we have. Different manuscripts have been published, different papers, and we also have a patent. I have a patent back in my home country, and also we put a patent last year here for Amber, and we are planning to do more patenting and more publications. So, if you want to think how Amber works, Amber takes the whole wastewater from your households and then turn it to energy, turn it to water, and turn it to compost. And it can be used in different applications. It depends on how people are going to accept the wastewater. So Amber will have an app, so you can actually see Amber on your phone, see how it works, how much energy have been produced, how much water have been treated, and also if you want to compare Amber to other techniques and technologies that is out there, you can see that Amber have a good high quality of water. No excavation is needed, no drain field is needed for Amber. No regular maintenance because Amber is a smart system, so it can take care of itself. It's very user friendly because we will be controlling everything, and it's been designed to take care of itself without the client to need to be involved. And no chemical usage, which is really important because we are trying to be more sustainable. So this is our team. You know me by now, hopefully. My advisor, Dr. Walker, who previously taught. Mr. Samuel Whitman, who is a graduate student of computer science. He did a lot of stuff on the control system of Amber. And Mr. Miller, who is our collaborator from a high school. And he's doing a great job. He manufactured the second version of Amber and also all the membrane housing forms. So Amber has garnered more than $170,000 right now from different resources, and we appreciate that. We have a good collaboration with all these organizations and companies, especially with steel. And we are planning to actually get more funding and proceed with the development of Amber. So our potential customer will be decentralized houses that they don't have access to central soil system. It will be small communities, remote area like army bases, ag confinement industry, and also nations with water shortage that I'm sure you know by now which countries are suffering. So the market value just on the decentralized houses will be $3.9 billion. But it's a lot bigger when we go to ag confinement, but this will be our beachhead market that we are going to start with. So Amber needs a reuse certificate, which is called NSF ANSI 40 and 350, which is for wastewater treatment that they are trying to do reuse and recovery. So, but not all of the states need that. Some of them, like South Dakota and Nevada, which has a big water shortage, they don't need that kind of certificate. So we are going to start in our state and also in some states with water shortage that they can be a good start for Amber, like Nevada. So when we talk about the system like Amber, we know that we are not the first one. The other like technologies, they have been trying to pursue this goal, and they've been doing a good job. But the problem is either they are using chemical, they are consuming energy, or they need heavy construction, which Amber doesn't need. And also, if you compare the price, it's a lot cheaper and more frugal for Amber. So if you compare Amber with advanced competitors, which you see here, Interval, Hydroloop, and stuff like that, and other companies like that, and also even with the septic system, you can see that Amber will be a great competitor. So if you have a septic system and you are trying to replace it, you can see that the extra amount that you will probably need just to buy that price is just to buy a storage tank. It's not for the whole construction and putting the drain field in and stuff like that. It will be $20,000 when you want to actually put a new septic system in place. So Amber, even with just a tank, Amber will compensate for that extra money in 2 years because it will help you to save on water and save on energy. This is our manufacturing plan. We are trying to do assembly here in Rapid City, some manufacturing in other cities and around the state. So we are trying to create jobs in the state, and Amber will be in-house system, and we will be just exporting the system to other states and also to other countries. So we will produce a small-scale residential system for just one household, and also a complex system which will cover more population. And we will scale it up. It's easy because it's a cascade system. We can easily scale it scale it up, and we can cover a wide range of population and application because amber can also be used in different industries. So our path forward will be to run and operate that amber commercial MVP hopefully soon, that everybody can go and look at it and see how amber works. We formed the Amber Aqua LLC, so that system is done. We are applying for a proof of concept funding just to help us to manufacture a public demonstration of Amber. We are trying to garner more funding for Amber, either from private investor or from agencies like NSF or SBIR. And we need to get that reuse certification because Amber we are planning to serve in other states with more regulations and in other countries. So thank you for your attention, and I will take any question that you may have.
So we got time now for a brief question while we set up our next week.
Okay. So say somebody buys this at their house. How long do the different components, are they expected to last before they have to replace different components?
So like any other technology, there are some pumps and stuff. Hopefully they will break down because we are trying to do more reliable stuff. But beside that, you need to replace the membrane every 5 years, which is almost around what people do for their septic system, like maintenance, which is 3 to 5 years. Probably by the law of the our county is 6 years. Most of the time that you need to complete this. But with Amber, it will be 5 years, just to replace the membrane.
Yeah, so you focused quite a lot on the water treatment aspect of it, but then you touched a little bit on some stuff like the biogas, and very briefly on the compost situation. And it gets me thinking, what are the main goals of Amber beyond just water treatment? Like, what kind of clientele do you currently have or aim to have?
So the aim is to increase sustainability. So we are trying to not to use any chemical in Amber, which will add to the pollutant that we are using for wastewater treatment. That's one thing. And we are trying, the goal is to turn that biogas into electricity, so people don't have to deal with it, and also it will be even more sustainable. But I think when I developed this system and we worked on it, we focused on turning wastewater into potable water, so we can actually drink it. Maybe we don't need it here, but in some parts of the world, they need it really bad, so they can actually drink, just reuse and recycle water that they are polluting. And I can drink it from, so I don't mind. And that's the goal, I think, just to provide everybody with water if they don't have access to clean water, so they can actually, at least they can have some water source that they know it's not going to make us.
Well, I do think there's more here than just water treatment.
To me, it's more than that. It's going to help a lot because then it will protect other sources that we are polluting. If you think about it, we are polluting the soil, we are polluting the surface water, which is clean, but we are polluting it to wastewater. So to me, yeah, it's more than just treating water.
So in the interest of time, we'll
Just real quick.
Yeah.
On the paper that you wrote, is that public?
Yeah.
If it's possible, I'd like to.
Okay, we can get you copies of it for sure if you can't access it online. So we're going to go to our next speaker real quick, and then we'll have time at the end for milling around and answering different questions. Our next speaker is Sebnem Ozbek. She's a mechanical engineer by training, doing her PhD in chemical and biological engineering. She's going to be talking about a problem that's called cold spraying that you might have heard of with companies like BRC here in the local area that do metal cold spraying. And Sebnem's working on trying to pivot this technology to cold spraying with polymer materials. So we do a lot of polymer work in our group. So Sebnem.
Thank you. Thank you for being here. Do you hear me or should I use a microphone? Can you hear me? Raise your hands. Yes. Okay. I'm Sebnem, if you don't know me. This is my 5th year in PhD. Thank God I got my candidacy, so I'm getting ready to graduate. I'm from Istanbul, Turkey. And like Travis said, I got my degree in mechanical engineering, and I kind of pivoted to chemical engineering. I like to build stuff with our group, and I'm going to try to explain to you what is cold spraying and what we're trying to do. So I found this little video. It's really nice, I think. So when I was trying to see how can I explain cold spraying to people, I found this term 3D painting. So when people ask what cold spraying is, usually people tell each other, think of a snowball and like hitting that to a brick wall when it splashes and then kind of attaches on the brick wall. That's what we're doing with particles that are in micron levels, which you can think about your like hair. That is like around like the sizes that we're going at. So with cold spraying, we usually have a robotic arm, and we have a heated gas, which is already pressurized, and then we have a powder feeding system where we feed the gas and the powder inside a nozzle. This is a nozzle that is designed to be able to get our heat into kinetic energy, which gives us velocity. So if you think about sonic velocities, we're trying to get these particles at such high velocities where these particles are smushing up on that substrate, like on that surface. It's going to zoom into that surface level in a bit, and you'll be able to see that we're deforming the surface that we're cold spraying, and then we're deforming the particles as well. So what we're trying to do here is that we're trying to sustain all the mechanical properties of these particles and our surface. So cold spraying is used for repairing surfaces or additive manufacturing. I realized that my husband is a musician, he's a pianist. So as I started talking to him about my research, I understood that he might not everyone knows what additive manufacturing is. It's basically like if you think about milling and lathing, like when you have like a big bulk particle and you're removing stuff from it, right? You're making another product. We're doing the opposite. We're doing like adding on top of each other materials. That's what we call additive manufacturing. So cold spraying can be used for a lot of things, and I'll go deep into those as much as I can. But the main idea is that it is cold in terms of the melting temperature of these particles. So we're not melting anything. So we call it, it's still at solid state. So we're not changing the phase of the particles. So we are not causing any oxidation because of the high temperature. Since we're smushing these, we're keeping the mechanical integrity of like these particles and like these surfaces. So there are a lot of things that people can do. I found these videos on GE's YouTube channel. They had a lot of nice videos. I stole a couple of them. This one is, you see the cold spray nozzle here. You might not see the powders coming out of the nozzle because they're so high of a speed, and then it might be very thin particles coming out of it. One thing with cold spraying is that we have very small amount of particles coming out of the nozzle. We still can use it for larger areas, but it might take longer times. But for them, it apparently took 9.5 minutes to be able to do this. This is on metal. So people know how to do these things with metal powders on metal substrates. When I say substrates, I mean the surface that I'm spraying, basically. they're having issues with spraying metal onto polymers like plastics, or spraying plastics onto metals and vice versa. So that's where we come into play. I found this another nice video where they are using 2 robotic arms to be able to have 12 degrees of freedom, meaning that I can change my angle in 12 places and they can cold spray in larger areas. Like I said, we use cold spraying for a lot of things. The reason that we can use for it a wider range of application is that if you look at this graph here, it just has my particle temperature, and it starts from 0, and then it goes to 14,000 degrees Celsius. And then my particle velocity is here from 0 to 2,000 meters per second, so it's pretty high. When you, this little box here is cold spraying, basically. It sits at the very low as temperature-wise, and it can get you a lot of velocities, particle velocity, meaning that you can smush a lot of metals or like a lot of different materials. That's what it means, basically. And when you look at other thermal spraying methods, you see that they go up to higher temperatures. So you have to vaporize or atomize the particles that you're using. In this picture here, they use cold spraying to be able to repair a part with nickel coating. And here I wanted to show you that you can have a nice surface finish with different metal on top of each other. And in here they mostly use it for airplanes, like if you have an older parts of machine, you can cold spray it and then repair it and then use it again. When I say people like, I want to do cold spraying of polymers, and I know why I wanted to do, but I had to come up with like a lot of ideas to get people to understand me, like what I wanted to do. So I have a couple of possible applications for like why I would want to do this. Batteries is one thing when you need to like lay a thin layer of material on the anode or cathode. Cold spraying, I think, is a good application because right now most of them are still using solvents which are not environmentally friendly. You can use to make surfaces super hydrophobic, meaning that it repels water. It doesn't like water. So think about your windshields and like your car windows when the water just like dribbles. You might want that for a lot of applications. So you might have to you might want to spray a couple of like micrometer thickness of polymer, and that would give you anti-fouling for like the marines, and then when you have a ship in the sea or an ocean for like long periods of times, the algae or like sea living organisms are gonna want to attach on there and like corrode the surface, so you can kind of inhibit that from happening. And then for parts like in automobiles, like rather than trying to overmold on a difficult geometry, you can just spray polymer on a metal so that you don't have to go ahead and to try to overmold. Have you ever heard of VRC metals? Yeah, so they started the End Lab, if I'm not wrong. But they have a really nice cold spray setup system, which is like huge. This is like a room. It looks different right now, but this is the picture I found online. But they were nice enough to let me use their setup. But their setup requires a lot of powder, a lot of things, and like they use a lot of nitrogen to be able to push all those powders from their big powder feeders. Like their powder feed is like this big. So what we're trying to do is we're trying to build a micro cold spray setup. I'm sorry I don't have like pretty pictures right now because I'm trying to get my system to work. It's in a, you can think about it as like, it's in a cabinet, but every time I try, everywhere is powder, and it's like, I couldn't take pictures because I was just trying it today. But if you think about it, like, I would have my nozzle here, I need to have a gas heater, just like to heat the gas, and powder feeder. For some reason, I didn't think about it this way, but like powder feeder is the most limiting thing for me right now. I didn't know feeding like small particles would be this hard. I guess they go everywhere. But we did a lot of things. We're trying a lot of things. We're still changing the design, but I think this is cool. Our machinist, Maryam, talked about him, Kyle. He's helping us a lot, and he made us this nozzle. You can see the converging and it's not diverging that much, but like my nozzle inside here, we want to be able to see the particles flow and like get a high-speed image of the particles going through my nozzle. So he made us from acrylic, and yeah, I didn't have a question, and I'd like to get questions now. Thank you so much for listening.
Got time for a couple quick questions, so we'll set up the next.
I got a quick question. So I guess, what's your practice material? So I guess what polymers are you throwing? What's your substrate?
Yeah, I had polystyrene in hand, a bulk amount of polystyrene. So I started with that, and I'm still going with that. And then the substrates, I tried a bunch of plastics, and then I'm trying aluminum as well. That's where I'm having issues. I'm hoping I can solve it.
Thank you.
Yeah.
Another quick question? All right, well, if you think of any questions at the end, we can ask more. So our last speaker tonight is going to be Laura Brunmaier. She's a PhD candidate in biomedical engineering at Dakota Mines. She's going to be talking to you about the work that she's been doing in tissue engineering, specifically looking at the idea around vascular grafts.
All right, thanks, Travis. So I'm Laura. Most of my work, we're going to take a pretty big transition here. I like blood and blood vessels, and so that's what I'm going to talk to you about. This is going to be like a really high-level overview. If you have questions, feel free. I just want to give you an idea of what I'm going at here. So, as some of you may know, heart disease is a really big issue worldwide. According to the World Health Organization 2019, 17.9 million people suffer from cardiovascular disease of some type every year. And worldwide at that time, this is 85% of deaths, predominantly stroke and heart attack. The problem here isn't that we're kind of unhealthy, but it's how do we treat this? What options do the surgeons have to treat these things? And a lot of times they're able to go in with a stent and open up the blood vessel by putting in a piece of metal basically to keep it open. But if you have a very diseased cardiovascular system, that won't always work. And then they'll have to take a vessel out of your body, and then they bypass it. They actually sew it in. It's like a hole punch. They sew it in, and they try to get past that occluded area on your blood vessel. But to this day, that's really like the gold standard of how they treat this. So people with diabetes or advanced age, they might not have suitable vessels for this type of procedure. We don't have a vessel that we can go in the operating room and take it off the shelf and sew it into someone at this point. We do have some people who are working towards making vascular grafts out of natural polymers, which is my goal out of this. I don't want to use the synthetic things that we use in the lab. I want to use things that you would naturally find in your body or in nature, depending on how these things kind of shake out. But first, I want to give you an idea of the different types of natural polymers that are used. So we can look at autologous grafts, auto meaning self. So like I already referred to, they go in somewhere in your body, maybe your arm, probably your leg. They take out a blood vessel and they sew it in. But when you move from your heart to other areas of your body, that tissue that makes up the blood vessel changes dramatically. And when you put it into somewhere that's used to high shear, high pressure, it doesn't always hold up well. So if you do the math on autologous grafts, about half of them fail within 10 years. And if you consider people in their 40s and 50s getting these grafts put in, you probably end up on the table at some point in your life, which is very unfortunate. Like I'd already alluded to, a lot of times they're not always available. We have used xenografts, so that's when we go to another species, so cows or pigs, take their blood vessels out, put them in a body. Those also don't always hold up very well. And then we do have an option of allografts, so you're looking at same species in that case. So if we go into another person, you run into immune issues. Are we taking all the cells out? Are you going to get inflammation? So it's not an easy answer for this. Synthetic polymers are used in the body for blood vessels that are larger than 6 millimeters generally. That does not include anything on the heart. So in your neck and like your trunk area, if you need something put in there, these hold up okay. So two types is Dacron and EPTFE. So EPTFE, similar to Teflon, but it's expanded, so it's much softer. And then Dacron is that woven material you can see in the top there. They're very strong materials in general compared to a blood vessel. And so you'll have a difference in the material properties of it, which makes your cells mad a lot of times. So when they go from a stiff substrate to a softer substrate, they may not behave the way you want them to behave. Another thing is proteins absorb from your bloodstream, and that can affect thrombogenicity down the line as well. So I'm going to go back to this picture here and point out a couple things. So this would be like a triple bypass technically. You have your heart here, we have a saphenous vein graft put in, and right off the aorta bypassing your right coronary, and then another part of the saphenous vein here bypassing another major artery over your heart. The intimal thoracic artery is a very typical one. That's actually like in the tissue of your rib cage, and the surgeon goes in and kind of carves it out. Those hold up really well because it's already part of your arterial system. It comes off pretty close to the aorta, so the tissue's used to that kind of pressure. But when you take the vein out of your leg, for example, and you put it over your heart, it's not very happy. Those cells aren't used to that. There's a lot of reconstruction that goes into those blood vessels if it's at all possible. The reason that we take those that vein out of your leg is it's pretty close to the surface. We can go in with it's called an endoscope, and it's like a little circle. It sears all the tissue around it. They can harvest it without opening up your entire leg, which is really nice. You like don't want scars. But it's long, and so they can do multiple bypasses. I got to witness one that was, the guy had 5 bypasses put in, all from that one saphenous vein, which is pretty impressive, I guess. So this is our kind of an idea of what we're going after when we're trying to build this blood vessel. I put some really cool pictures of the tissue, like a cross section of it. So it's not just one uniform tissue. When you look at an artery, there's actually a ton of layers here, and the orientation within those layers actually changes, and that will add to the mechanical properties of this tissue, which is really important in the artery. So I made this crummy little cartoon here to kind of give you an idea of the different layers, because not all of us are used to looking at tissues, but we're really shooting at 3 different layers. Those can break down into sub-layers, but we really just want to keep it simple, and if our mechanics need it, then we'll move forward from there. There's no point overcomplicating it. An important part is the intima, so that's the blood interface. We have a couple different strategies that I'm not going to dive into the details there. The medial layer is really where the smooth muscles come in. You have smooth muscle cells there, but then the fibers are actually circumferentially oriented. So when you have pressure produced from your heart, it expands, and then there's recoil there. There's different types of proteins there that help with that recoil, which are not the easiest thing to work with in the lab. And then the adventitial layer is where your nerves, other blood vessels will come in, and there's kind of a random orientation depending on what kind of stress the tissue's under. So this is our first attempt at a very small prototype. We used a wet spinning method. We use a lot of different methods to process some of these materials in the lab to look and see what do the fibers look like, how can we handle them. So this was a wet spinning method with collagen. We made this really neat long fiber pretty easily, wrapped it up in a circumferential direction around a stir rod, and then we were able to coat the outside of it. Actually, I was really proud of this thing. I was really sad to get rid of it, but I had to eventually. So there's some actual measurements of it. It was just a tiny little guy, but we were able to take it in for SEM to look at the actual fiber orientation. This one, unfortunately, is too small to do any real mechanics on. It was really just a proof of concept showing that like this is one method that we were able to do in the lab pretty easily. These are some of the SEM images that I get from the collagen alignment. So collagen 1 is probably one of the most predominant proteins in your body that makes up your tissues. It's really good at, like, if the fibers are going in a longitudinal direction and you stretch it, it's mostly for tensile strength. Super easy to orient. As you can see here in our SEM images, we have really nice long fiber orientation. I apologize, you can't see those scale bars. But we were able to reproduce this pretty readily. If you're familiar with SEM, I know there's charging. We're getting there. So, as I mentioned before, the intimal layer is your blood interface layer. I got really interested in why these grafts in humans don't endothelialize, meaning we can put a graft that we make in a mouse, and that entire blood interface will be covered with cells. But when you put that same thing in a human, the middle of it, as shown here, you don't end up with an endothelium, which is a problem because the host isn't actually assimilating the tissue for one, but you're at risk of different blood disorders causing thrombosis or embolisms because blood likes to stick to stuff. That's kind of the purpose of it. So I found this paper, and it was kind of an inspiring moment for me, I guess. They use actually synthetic polymer. These are blood vessels growing through their synthetic polymer. I think it was in like a mouse or something, but they implanted it into the blood vessel. Theirs is a very porous material. They did that so the cells could infiltrate it because the cells can't actually break the material and remodel it. So you can see that the cells came through and grew little capillaries through here. This was important because then you can actually get that post-infiltration into whatever it is that you're implanting into them. But I'm bringing this up because this is what led us to building this device here. So Kyle Miller, as you guys have heard from the last two presentations, is our machinist, and he built this for me. This is, I don't know, model like 40 or something like that now. This is the current one that I'm using in the lab. So we built this device to be able to implant our graft into it, into one of those parallel channels. You can kind of see here, I use some food coloring, if you can see it. So we put cells into one channel, we implant our graft into the other channel, and because we don't have an animal model at Mines, we can actually use this device to biologically characterize our graft and see how human cells are actually interacting with it, as opposed to animal cells, and know if there's adjustments that need to be made before we move forward and have to come up with all that money to do those trials. So this little guy goes on to our microscope shown here. It's in an environmental chamber so I can keep the cells happy, hopefully. And then we can track this over time to see how the cells are interacting. Which I have a nice little cartoon here. This is one of my old models. This is the prior one to the one I just showed. So basically what's going on in these channels, I put my graft in one side, we put cells in on the other. The cells will attach, and that graft can diffuse certain chemicals, you could say. They'll diffuse across the gel medium. We probably put like a collagen gel there. They'll interact with those cells and cause sprouting or angiogenesis if you have any bio background. But in the lab, we can cause these cells to sprout, and they'll grow towards that graft because they follow a chemotactic gradient. And we can look and see, is that the lumen area shown here, is it actually endothelializing? Because if we can get endothelialization from within the host, that's actually a really huge win in the field. But it allows us to go forward with really strong preliminary data, go for grants, or be able to justify an animal model, or hopefully eventually clinical trials. So that's the idea of the device there. That's one of the uses. I have a couple other projects that are going to that use it in a completely different light. And so that's kind of a high-level overview, and then I had to thank some important people here shown, and then some of our some of the foundations and different things that gave us money. So at this point, I'll take any questions.
Maybe a couple quick questions for Laura before we open it up in general.
I guess another quick question. I don't know how quick it'll be, but like, are there any certain properties that the sales are looking for from your graft material in order to endothelialize? Do you need to have porosity, or do they kind of do that on their own?
So because we're using all natural polymers in this, they can remodel it. So they actually secrete different proteinases that'll break down that material, and then as they're going, they can reconstruct it, but that way they can navigate through it.
So that's the advantage of using
That and FDA.
Yeah, that makes sense. All right, thank you.
Yeah. Any other questions? There's a couple different ways. I mean, the first is, are they actually attaching and growing, because that system allows us to induce flow, so are they able to attach under flow? We can go through different stainings to see if they're still maintaining an individual phenotype. That will tell us some of what, if they're actually happy or not, and if they're actually proliferating. So a lot of it in bio in general is kind of qualitative. And so these first steps would be primarily.
Let's thank our speakers again for tonight. So thank you for letting us come and talk a little bit about the different work that we do in our group. You got to see some wastewater treatment. You got to see some polymer processing. You got to see some tissue engineering tonight. And those are just a few of the projects that we have going on in our group as well. We didn't get to talk tonight about things like using magnetic fields to move particles around inside of suspensions, or how we could synthesize our own monomers to create an object that is structurally sound, and then I throw it into a bucket of water and it'll completely degrade away. So we do, along with other projects that we have going on as well. So what I really like to do with the group is we like to learn something in one project and try to take the fundamental knowledge of that, whatever is happening, and try to pivot that over to a completely different project, be able to disrupt whatever area that is. And so then we don't get shy about going into any area that's out there. And so we're often a little bit naive when we go into these areas, but we get to learn a lot. We often ask really simple questions that the people that are in that area for a long time haven't thought to ask these simple questions. So with that, I appreciate you guys coming out tonight. Most of my group is up here in the front. We do have some people in the back, but if you have any questions, we'd love to talk to you guys more. Thanks again.
Thank you for coming, as they've said. I just wanted to let you know that we do this every third Tuesday, so next month, the presentation is on October 18th, excuse me, and we will be hearing from the National Security Innovation Network at Mines, which is a partnership with the Department of Defense. We're going to have, I believe, 3 presentations from students that are currently working on projects with Ellsworth Air Force Base and what they've done, how they're progressing. So that should be interesting too. We hope to see you next month. Thank you.